This is the quick review of the gas chapter. Make sure you have this page written out in your own handwriting. Make sure you have little notes to yourself about units, like especially in this section, you know, that like that P should be in ATMs. Make those little notes to yourself to remind yourself what the units are going to come out to be. Up here, make the little note about how both those P's have to be the same unit, but they don't have to be ATM. Make a little note that everything has got to be in Kelvin. You probably want a reminder of these different ATM pressure units. And don't forget, do a round or two practicing with this temperature conversions. Now, over in here, this lower section, the P total, that's a really easy equation. It's fast and easy points, so make sure you know your P total. You just add up all the pressures of the gases. You may have to use this PV solved for P for each of the gases. You may have to do that. Or you may just be given them. Make sure that when you're adding them, all of them are in the same units. So this, if this is ATM, then this has to be ATM, and this has to be an ATM, and this will come out in ATM. Make sure you know how to calculate mole fraction from moles or from grams. Remember, if you've got to get grams into moles, you just use the molar mass. So this would be the molar mass of one thing, and then that's the molar mass of two things added together. You don't have to use this one on this test. Over here, also don't forget that if you know the mole fraction of something, you can multiply it times the total pressure, and you can get A. Do not forget, STP for gases is standard temperature, it's this value, and standard pressure is this value. And in big letters, write R for yourself out with the units. Make sure you have a good idea of these, just different ideas of how gases behave. Maybe make a little summary of yourself of this page. Remind yourself about ideal gases. What are ideal gases? And I'm going to make a little note that wasn't on here originally. It's on my other notes. But things are most ideal when they have a high temperature and a low pressure. Again, that's that temperature practice. Make sure you've got that. And then all of this is just lots of practice with the math. So just make sure you can do all of those. There's examples here. Is the molar mass problem. There's 2 using molar mass, and then there's 1 using density. Like you can solve for density. You know, just because this problem has you solving for molar mass, maybe this problem, maybe you'd get this one on exam or test. I'm just saying, if you can work a problem one way, we're assuming you can work and solve it for any of the variables that are over here on this side. And then if we go on up here, what is STP? Again, the reminder on STP. Make sure you know about this value here. This is called molar volume, and it's a shortcut when you're doing math with gases for equations. So if you have an equation and it's at STP, you can say that that's related to 1 mole, and you can skip having to use the PV equals nRT equation. If you look down here, here's some examples of different ways to get around having to do PV equals nRT the long way. So here's a faster way of doing any kind of a reaction problem. You're going to take the liters of the gas, and then again, that's that standard molar volume. Then these are the coefficients in the reaction, and that's the molar mass of zinc. Then over here, there's another fast way to solve problems. It only works if everything is a gas, not just one thing. Everything in the reaction has to be a gas that you're looking at. And in what you can do in this case, this does not have to be at STP. And in fact, since this equation is not at STP, you cannot use that 22.4 liters. So 22.4 only matches with STP. But this one has its own values, which are great. But the shortcut here is that since we have an all-gas reaction, nitrogen is a gas, oxygen is a gas, and this as a gas, it tells you in the problem that this one's a gas. Then you can do this shortcut with the liters. You can take the liters of the first problem, and then it's right here. And then you can use it's the molar ratio, but you can actually use it as a liter ratio. It's craziness. But those are the 2 coefficients. And get right to the answer without having to do all of that math. So there's some more examples, practicing doing that. And then this is the section where you can practice either a mole fraction or the idea of mole fraction. That's just however many, purple dots are in the total number of dots. So that's pretty easy. And then you can use this equation with mole fraction You can either have the total pressure and solve for the partial, or likewise have the partial and solve for the total pressure. Make sure you keep track of exactly what it says it is. And then also, this is so easy, just with saying, you just make sure everything's in the same unit. You just add up the partial pressures. So there's some practice with that. Here's some practice of using a gram amount and then using the formula here, the molar mass, to get to the pressure. And then here's using mole fraction if you need some practice, mole fraction. And then here's some practice using this equation. If you know the partial pressure, and that little label on the bottom tells you whose partial pressure it is. And if you know the total pressure, you can also get to the mole fraction, or you can get between any of these different little variables that way. And last little bit about diffusion. It depends on size and temperature. Anything at a high temperature is going to be moving faster than some things at low temperatures. Effusion's where you go through a tiny hole. Diffusion is where you just have two open areas, two open like flask or containers that don't have tiny holes that are close to the size of the molecules. They just have a big open space. And it's how they mix. Ultimately, regardless of the hole size or not the hole size, if it's a closed system like down in here, then they'll end up being equal. They always end up equal, but it's kind of we showed this on the simulations, it's kind of like a constantly changing thing where gases keep exchanging back and forth, but they end up being approximately equal. At any point in time, they could be almost equal or equal. And there's another picture of effusion, and you can see how it's also a purification technique. They use that with radioactive gases also to purify them. And you just need to know that the ones that move slower are going to be the larger molecules, and the ones that move faster are going to be the smaller molecules. Make sure you can pick out the fast ones, if you looked them up on the chart, versus the slow ones. And that should be the end of that section. Go back and work some of these different problems in here.